Hey, welcome back to Famama Physics. In this video, we are going to talk about nuclear energy levels in radioactive decay, and I'm going to squeeze in a little bit of pair production and annihilation there, just to complete some little, just little loose topics in the chapter, group them together and such. So nuclear energy levels, hopefully at this point, you have looked into line spectra. You have a little introduction on quantum mechanics as well as the photoelectric effect, and that specific jumps of energy levels for electrons, specific energy level jumps correspond to specific frequencies of light either emitted or absorbed by the electron themselves. So we've introduced the idea of these discrete energy levels, which then we are going to apply for nuclear energy levels because we see very similar patterns. So that's what this first part of this video is going to be about. And I'm going to do a little introduction here. So what we have observed is for specific decays like alpha and gamma decay. For gamma decay, this is easy. You have a very excited nuclei, which then goes to a less excited state, and it ejects a gamma particle in the process, or it ejects a photon, essentially. And afterwards, we detect that through these gamma decays, this gamma particle corresponds to energies that are very specific, so very discrete energy levels. Very specific energy levels, which then correspond to discrete energy level transitions of nuclei of our excited nucleus, okay? So this guy might go from a high excited state to a lower excited state in which the energy difference is very specific. It corresponds to this photon of light that's emitted in relation to the Einstein-Planck relationship, okay? So that's for gamma decay. For an alpha decay, on the other hand, we know that we have a parent particle, we have a parent nucleus, and through the alpha decay, it ejects an alpha particle, and that's the only thing it ejects, which means that after this alpha particle leaves, this particle is going to move in the other direction, in which the total momentum is going to be the same, assuming that there are no other external forces acting on our system. So according to Newton's third law, it means that the momentum of this big particle going this way versus the momentum of the alpha particle in the other direction, the magnitudes are equal, the directions are opposite, and we find that for these alpha decays, they also these alpha particles will be ejected with specific kinetic energy levels, which then, of course, will correspond to specific, the alpha particle as well as the kinetic energy of this particle ejected sums up to very specific energies, which then correspond to specific energy level drops at the nuclear level. Okay, so very similar in concept to electrons, but this is talking about the nuclear energy levels, specific nuclear energy levels. Okay, so that's for an alpha decay. Then you might be wondering, what about for beta decay? Well, if you recall, in a beta decay, whether that's a neutron to a proton or a proton to a neutron, either way, you're going from a neutron, let's say this is beta minus, you get an electron, but you also get a neutrino, okay? An electron neutrino, anti-neutrino in this case. So there's going to be three particles that are coming off of one another. So you essentially have three particles going off. As long as after you sum up all the momenta, they are constant in before and after in all the different directions, then you do have a case where you can try to look at different energy levels of this nucleus. But the problem in determining that is the fact that your electron is moving off. It could have a range of different energies depending on how the momentum is distributed amongst these particles. So what we detect is that in a beta decay, the electrons can have a various amounts of energy, in which the maximum energy here assumes that your neutrino has a zero kinetic energy at the end, which is less likely to happen, which is why the graph kind of tapers off here. So based off of these findings, it's very hard to do that. Then you might be thinking, well, if you found the antineutrino, we know we can detect this the big particle, the remains of the parent particle. It's actually very hard to detect the neutrino because it only interacts with matter very little. Because right now, currently, you have thousands and billions of millions of neutrinos flying through you, and we just can't detect it, which is why we have big setups in Antarctica. I forgot the name of it, but essentially you have these detectors that are packed underneath the ice, and which we try to detect neutrinos coming from outer space, and we get one interaction in a very long time. I don't remember the numbers, but essentially it's very hard to detect these neutrinos, so it's very hard to find the total kinetic energy of all three particles, which is hard to say, hard to talk about discrete energy levels for beta decays, but definitely for alpha and definitely for gamma. Okay, so let's erase this first. So I did a little bit of search on this neutrino detector in Antarctica. It's called Ice Cube. I forgot about it. So it kind of looks like this. All of these sensors are underneath the ice, and the reason why it needs to be in Antarctica is because to detect the neutrino needs to interact with matter, and the one way we can do that is for it to interact with the water that's in ice. So when the neutrino does that, it creates these other charged leptons, which potentially can travel very fast in ice, potentially faster than the speed of light. It's just the nature of how these particles work, and so when that happens, it gives off something called Cherenkov radiation, which then we are able to detect and to note down that hey, we've detected a neutrino. So that's kind of how it works, and when we do detect a big shower of neutrinos, it usually means that some astronomical event is happening, and we are picking up the decay products of whatever is happening far away. So could be it might have to do with dark matter or other things that we are other observations we're making related to astrophysics. So very interesting stuff. So if you would like to, you can look into the Ice Cube Neutrino Observatory. The site is, I don't know, I'm having trouble with accessing the site, so I'm just pulling up some images here. So there you go, some interesting thoughts about the neutrino. So if it weren't, and because of how the kinetic energies don't match up in the beta decay, which is why eventually this guy, Wolfgang Pauli, attributed the fact that this missing amount of kinetic energy has to give rise. There must be another particle in the decay products in order for everything to balance out, for the momenta to balance out. Okay, so based off of these observations, not the beta, of course, beta decay, but with these two decay, we find that nuclei have specific energy levels, so we can use our experiment to look into these energy levels and use that for further predictions. So we're going to do the opposite. We have the energy levels. We are going to, example 1, in the gamma decay of magnesium depicted in the graph on the left, calculate the wavelength of light emitted. So we have a jump from this from 5.24 electron volts to 1.37 electron volts. So with this jump, we are going to find the difference in the energy and use that to calculate for the wavelength of light, which we can use the Planck-Einstein relationship here to figure out the wavelength. Wavelength is therefore EhC over E, which is the energy. For electron volts, I get 3.87, and I'm going to multiply this by 1.6 times 10 to the power of negative 19 joules per electron volts. I get 6.192 times 10 to the power of negative 19 joules. And to figure out the wavelength, I'm going to do that right here. So I have Planck's constant, 6.63 times 10 to the power of negative 34. And the speed of light, 3 times 10 to the power of 8. I am doing a bad job with units. The energy here is 6.192 times 10 to the power of negative 19 joules. And this gives us 3.212 times 10 to the power of negative 7 meters. So rounded to 3.2 times 10 to the power of negative 7 meters. So in this example, the gamma decay of magnesium is depicted on the graph on the left. So we're going to use this graph to figure out the wavelength of light emitted. So with a drop of energy from 5.24, don't forget this is mega electron volts, so reading that very carefully, down to 1.37 mega electron volts. So finding that difference there is going to be 3.87 mega electron volts, and to get that in joules, multiplying by 1.6 times 10 to the power of negative 19 joules per electron volts, and to get rid of the mega, we gotta multiply this by 10 to the power of 6. So this ultimately gives us 6.192 times 10 to the power of negative 13 joules. And to figure out the wavelength, we're going to use the Planck-Einstein relationship here. So relating that energy to the wavelength instead of frequency, meaning to get the wavelength, we need to rearrange it so I get hc over energy. So h is our Planck's constant times the speed of light, and all over the energy we found in the previous part of this question. This is going to give us 3.2 times 10 to the power of negative 13 meters. So that's 2 sig figs. And that is it. So there we go. Okay. And it checks off over there. All right. So that is nuclear energy levels. You know what? I'm going to split this video up. Next video, I'm going to do pair production and annihilation. This is too long. Okay. All right. Anyways, I thank you for watching and bearing with me with all of this stuff. And hopefully you'll be interested in looking into more about Ice Cube. Anyways, I wish you good luck. Please stay tuned for pair production. Fan Mama Physics signing out.